Hey everyone, welcome back to another video by Camroom 5. In today's video, we're starting with the concepts of further equilibria, and we'll touch upon the concepts related to acids and bases, but we'll first start with the self-ionization, also known as the self-dissociation of water. So when we begin talking about that, we need to understand that water, unlike many other molecules, water has a tendency to release H plus and OH minus ions, thereby acting as acid and base both. So when we talk about the equilibrium constant for water, the H plus and OH minus ion concentration comes as the numerator, while the undissociated water would be the denominator. But we need to understand that it almost remains the same. The amount of water dissociating is very small, so the amount not dissociated is pretty much the same as the original amount. And this leads us to the concept of Kw constant, which means the self-dissociation constant for water. So Kw is the self-dissociation, also known as the self-ionization constant for water, which is equal to the product of the H plus and OH minus ion concentration. When we try to understand this idea, we need to know that this value stays constant at 25 degree at 1 exponent minus 14. And this is the product of the concentration of two things which are in 1:1 ratio. So 1 exponent minus 14 is technically the product of two same things, or you can say the product of x squared. So the amount of x is going to be the under root of 1 exponent minus 14. So the concentration of H plus and OH minus is same in distilled water at 25 degree, which is 1 exponent minus 7 mole per decimeter cube. Remember, this is 25 degree because this reaction is temperature specific. Because the dissociation of water is actually an endothermic reaction, and based on temperature, higher temperature favors the forward reaction while lower temperature favors the reverse reaction. If you notice on the left hand side, if the temperature of the beaker would increase, which means more forward reaction would happen, so more dissociation would happen. So high temperature favors more dissociation of water, and where more H2O dissociates, more H plus and OH minus ions would be produced. This means that the H plus ion concentration and OH minus ion concentration would increase. So Kw would not be 1 exponent minus 14, it would be more than 1 exponent minus 14 because H plus and OH minus are both increasing. Similarly, H plus and OH minus ion concentration won't be 1 exponent minus 7, they would both increase equally and they would be more than 1 exponent minus 7. The whole point of this argument was that at very high temperatures, the pH and pOH of water will also be a little different than 7. Now this leads us to the question, what's pH and what's pOH? In this chapter you will see the small letter p a lot of times. Small letter p means power of. Conventionally it means power of. Mathematically, wherever you see small p, it means negative log. It could be negative log of anything. Small p is used for the expression of exponentially small quantities, exponentially small values as positive integers. For example, very small concentrations of things can be represented as very simple whole numbers using the concept of negative log. Not necessarily log number, just positive integers. You know Kw is the product of H plus and OH minus ion concentration. In distilled water, both these concentrations are set at 1 exponent minus 7. And this is specifically for distilled water at none other than 25 degrees Celsius. So pH is equals to negative log of the H plus ion concentration. So it's 1 exponent minus 7's negative log. So pH is 7. Similarly, pOH is the negative log of the OH minus ion concentration. That is again 1 exponent minus 7's negative log, so 7. Now I want you to look at these two scales. On these two scales, I have the concentration of H plus and OH minus ion. And I want you to remember that the product of these two ion concentrations should always be 1 exponent minus 14, because that is the value of Kw. I also want you to remember that the product of pH, no, the sum, not the product, the addition of pH and pOH is always 14. Imagine at 25 degree the concentration of H plus and OH minus is both 1 exponent minus 7 each. So when you look at these concentrations, you obviously know that their product is going to be 1 exponent minus 14. This proves our initial argument. At the same time, I also want you to remember how we find the pHs and pOHs. pH is basically the negative log of H plus, and pOH is the negative log of the OH minus concentration. So pH of distilled water is 7, pOH is also 7, and when you add that, you get 14. Nothing new about it. We call it pKw. That is simply 14. Now let's allow things to become a little more interesting. When the H plus ion concentration is negative 6, the OH would be exponent negative 8. And that is how when you find the pH, it would be 6 and the pOH would be 8. But you get the same values. If the H plus ion concentration is negative 5, OH concentration would be exponent negative 9. pH would become 5 in this case, and pOH would become 9 in this case. Similarly, for every decreasing OH concentration, there would be increasing H and vice versa. But their product concentration would always be exponent negative 14, and the sum of pH, pOH would always be simple 14. While we have talked about some ideas of acids and bases, it's a good time for us to understand how a Bronsted-Lowry acid and conjugate bases work. Basically, a Bronsted-Lowry acid is anything which is a proton donor. So when the bond of hydrogen atom with the other atom breaks down normally in a molecule, you receive H plus ion, which is the proton. A conjugate base is an interesting concept. It is basically the reverse of the acid, obviously, and it's a proton acceptor. Imagine this molecule of ethanoic acid where the bond between O and H atom is going to be weaker, and after dissociation you receive ethanoate ion and receive H plus ion. This entire portion of the molecule, which is later going to become the negative ion, this can be represented generally as A, while the H, which is going to be dissociated, is written next to it, so HA. After dissociation, this negative ion is your conjugate base, so it is the A negative, while the H is going to be written as H plus, obviously, so H plus. This negative ion represents the conjugate base, because if you think about this equilibrium reaction as a reverse reaction, the conjugate base can accept a proton and give you undissociated acid. This entire molecule is known as the undissociated acid. If we were to talk about the equilibrium expression for this one, it can be written as Kc is equals to H ion concentration, a negative ion concentration, which is your conjugate base, divided by the concentration of the undissociated acid. For a weak acid, it is immensely less, it is very partial that it dissociates, right? The dissociation, the ionization is very, very, very small. This means the concentration of the undissociated acid relatively stays the same because the percentage dissociation is hardly like 3%, 4% on average. That is why this Kc can also be called as Ka. Now what's Ka? Ka here means weak acid or acid dissociation constant. So Ka is equals to acid dissociation constant. Now, using this expression, I have something else to be derived. What is that? We know one thing for sure, that pH is equals to negative log of H plus ion concentration, right? So I can make H as the subject of this equation. H as subject of this equation. How would I do that? I know one thing for sure, that H plus ion concentration and the conjugate base concentration are in a 1:1 ratio, which means they are equal to each other, which means they are both the same. So Ka becomes H plus ion concentration square divided by the concentration of the undissociated acid. And as a result of this, H plus ion concentration becomes Ka times the concentration of the undissociated acid, and in order to cancel out the square, I put an under root. Putting this entire expression over here, I get pH is equals to negative log of the under root of Ka for any weak acid times the concentration of its undissociated initial acid. And that is an equation I would want you to keep in mind because we will later use it. Another very important concept is that whenever a weak acid dissociates to give you the protons and the conjugate base, if the weak acid is there, it means the equilibrium shifts or leans towards left. It means that more and more H plus ions and A negative ions will combine together to give you HA, because they don't want to stay as dissociated ions, they want to remain undissociated. So as a result, you can also say that this conjugate base is strong. Why is it strong? Because it readily accepts protons to give undissociated acid HA. I hope the weak acid idea is clear to you because we are going to use these equations next. Now this question says, write an expression for the Ka of the weak acid HA in terms of the concentration of the species involved. We have just done this, right? Ka is equal to the concentration of H plus and conjugate base A minus divided by the concentration of undissociated acid. The hydroxyl ammonium ion is a weak acid and the concentration is given 1 exponent minus 3 and the pH is 4.41. Calculate the Ka of the hydroxyl ammonium ion. Now for that, we know that H plus ion concentration can be found out by the antilog of the negative pH value, which is 10 exponent negative pH. Antilog of negative 4.41 is going to be equal to, let me do it, 3.89 exponent minus 5 mole per dm cube. So you have the H plus ion concentration. Now Ka is equal to H plus times A minus over HA. Since H plus and A minus are in the same ratio, I'm going to square them because they are the same thing, divided by the concentration of undissociated acid 1 exponent minus 3. When I solve it, Ka turns out to be 1.514 exponent minus 6. So this is my value for Ka. Now moving on, calculate the pKa. So pKa basically is negative log of the Ka. I'm going to take the negative log of this Ka value, which is 1.514 exponent minus 6. It's 5.82. Isocyanic acid is a weak acid. The Ka value is given. Calculate the pH. We have just done a simple formula like negative log of the under root of undissociated acid concentration times Ka. You have the concentration of the undissociated acid, which is 0.10 times Ka, which is 1.2 exponent minus 4. You solve it, you get 2.46 the pH. We can skip this part, it's not important for us right now. When concentrated sulfuric is added to water, the dissociation takes place in two stages, blah 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 blah. Ka2 is the acid dissociation constant for stage 2, okay. Right expression for the acid dissociation constant Ka2. So sulfate ion concentration on top, H plus on top, and HSO4 negative as the denominator. H2SO4 is considered a strong acid, where HSO4 is considered a weak acid. Suggest how the magnitude of the acid dissociation constant for stage 1 compares to Ka2. So stage 1 dissociation constant would be very much larger. I'll write it later. Very much larger compared to Ka2, because weak acids have a very low Ka, but strong acids have a very high Ka. Phenolphthalein is an indicator and is represented by the formula H-ion. H is the proton, ion is the entire conjugate base. It's a weak acid, right? The Ka value for phenolphthalein is blah 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 at 298 Kelvin. This indicator changes color at a pH of approximately 8.8. Calculate the ratio at pH 8.8. So Ka is going to be conjugate base times H plus concentration divided by H-ion. We have the ratio in this very equation, but we don't have the H plus. Let's use the pH to find H plus. H plus is equals to antilog of the negative pH, which is negative 8.8. So you can write it like this, or you can write it like 10 exponent minus 8.8. The H plus concentration is 1.585 exponent minus 9 mole per dm cube. Now since you have the H plus ion concentration with you, and you also have the Ka with you, how about we solve it and we find the ratio? We put H plus as the denominator on the other side of the equation, and when we solve it, we will get the ratio of ion negative over H ion. The ratio is 0.315. I hope these ideas are clear to you guys. In the next video, we're going to talk about buffers. Stay tuned.